It is part 2 of section 6.1, Solids of Revolution, the disk method. In the first part, we studied how to get the volume of generally shaped solids. And also we considered a strategy. First, you have to understand the solid, for example, by sketching. And secondly, you have to recognize the lower bound and upper bound when you try to get the area at each point x between A and B. Once you can express the area of cross-section, then you can integrate the A of x over A to B to get the volume. Here, we'll use the exactly same technique. However, we'll deal with special solids and solids of revolution. A solid of revolution is the solid generated by rotating a planar region about an axis. Now, let's see this example. The region between the curve y equals square root of x is moving from 0 to 4, and the x-axis is revolved about the x-axis to generate a solid. Find its volume. Here, the curve is now y equals square root of x. Now, x is moving from 0 to 4, and x-axis, so this blue region is rotated about the x-axis. Then we can see such a solid. And we'll use the exactly same technique. And already we know and we understand the solid, and x is moving from 0 to 4. And for each x between 0 and 4, we have to find the area of the cross-section. So AX is the same as now pi r squared, because it's a rotated solid, and each cross-section must be pi r squared. What is r? That is now the radius. So radius is now square root of x. So here this is pi and square root of x squared, which is pi x. So the volume must be from 0 to 4 and pi x, which is a of x and dx. So pi can go out, and integration of x is half x squared from 0 to 4. So we have 8 pi, which is the final answer. Quite simple. So you have to express the cross-sectional area in terms of x as a function of x. Then you can integrate the ax and over the interval to get the volume. Here we summarize the technique. The volume of the rotated solid is here integral from a to b a of x. Now the area will be pi r squared. So we have such a formula. And the method for the calculating the volume of solid of revolution is called the disk method, because the cross-section is a circular disk of radius r. Okay, let's see this example. Find the volume of the solid obtained by rotating the region bounded by the given curves. And rotation is about the x-axis. Let's visualize to understand the problem. Now that is y-axis, and this is x-axis. Okay, y equal half x plus 1 is straight line like that. That one. Now y equals 0 is the x-axis, and x0 is y-axis, and x 5 is here. Okay, so the region bounded by these four curves is that one. Now, this region is rotated about the x-axis. So for each x between 0 and 5, and we have to get the area, we have to express the area at each point x. So here now ax equal same as pi r squared. What is r? R is the height. So that one, half x plus 1. So here there is a half x plus 1 squared. From here, we can easily see that the volume is integral from 0 to 5, and a of x, that is pi and half x plus 1 squared dx. For this integral, I believe you can finish it easily. So try to find the final answer by yourself. Now find the volume of the solid obtained by rotating the region bounded by the given curves about y-axis. Okay, now rotation axis is the y-axis this time. Okay, now let's visualize the problem. Here there's y-axis, then there is x-axis. Now xy equal 4 can be given in this. Okay, I'll try to draw again. Okay, xy equal 4, that is here in this shape. Okay, that is the curve here now. And x equals 0 is y-axis, yeah, and y equal 1 is a horizontal line. That's 1 here. Y equal 4, this one, 4. So the region bounded by the curves is this one. Now it is rotated about y-axis. Okay. So here, for each y between 1 and 4, you have to find the cross-sectional area. It is rotated, so you may imagine that the solid is the other side, and each cross-section is a disk radius r, but for each point y, that one, the height is x from this equation, so that r equal, in fact, x, and x is from this equation, you can get 4 over y, right? So area at y, the cross-sectional area is same as pi times and r squared. So the 4 over y here squared. And here the volume must be integration from 1 to 4. Y is moving from 1 to 4. For each y, ay is same as now pi 4 over y here squared and ty. Okay, the constants can be here simplified, pi and 16, so that 16 pi can go out, and from 1 to 4 integration of 1 over y squared dy. Okay, antiderivative of 1 over y squared is minus 1 over y. So here 16 pi and minus 1 over y. Now evaluation is from 1 to 4. Okay, so 16 pi n. Okay, and ignoring minus, you can evaluate first with the low limit. So that is 1 over 1 is 1 minus 1 over 4. Okay, so if you simplify then that will be the final answer. Okay, volume by Wishes for rotating about x-axis. Here, once the region is not attached with the axis of revolution is far away, then there must be empty spot inside. So each cross section will be a kind of washer. So here area can be obtained in this way: pi r squared. Capital R is outer radius and small r is inner radius. So that pi capital R squared minus pi small r squared. That is area of washer. So it is called the washer method. Let's try to solve this problem. Find the volume of the solid obtained by rotating the region bounded by the given curves about the x-axis. Again, let's begin with visualization. Okay, that is now y-axis, that will be x-axis. Now here, y equal half x plus 1. Here that is y equal half x plus 1. And now y equal square root of x over 2. That is now given in this way. And here, that curve is this one. Okay. Now, is x equals 0 is y-axis, and x equals 5 is that one. So that region is rotated about x-axis. Then here, if we choose x between 0 and 5, then now this part will make a washer. So outer radius pi capital R squared minus pi small r squared will be area at x, the area of the cross section. So here, let's try to write down area at x. That is, capital R is half x plus 1. So there is pi, now half x plus 1 squared. And that is the area of disk area. But now, inner empty spot must be eliminated, which is now pi here, the squared, and small r. That is now square root of x over 2 squared. So the volume must be integral from 0 to 5, and now we can put pi outside, and then that is here half x plus 1 squared minus, now that is x over 2, right? So if you try to get integration for this integrand and multiply pi, then that will be the final answer. You can finish the computation yourself. Okay, we'll go to here the final problem. The region bounded by the parabola y equal x squared and the line and y equal 2x in the first quadrant is revolved about y-axis to generate a solid and find the volume of the solid. Okay. Now, this time we are rotating the region about the y-axis. We have to understand first the problem. Okay, try to sketch the problem. Okay, here, y-axis and x-axis, here now, and y equal x squared is given in this way, and now y equal 2x in the first quadrant. Okay, so that is y equal x squared, and that is y equal 2x. The region in the first quadrant is rotated about the y-axis. So now you can imagine the solid occupying that area, right? Okay, now start from 0, and you have to find that one, and we can get y-directional integration. So we have to find this point. How? Here, equalizing, we can find the value of x first. So y equal x squared and y equal 2x. Then from here, we can get x equals 0 and 2. That means that here, that x is 2 and y must be 4. Now, from 0 to 4, if you are selecting y, then now this will make, after rotating, it will make a washer. So the area of washer must be computed here. So ay, okay, a at y must be pi x squared. So that x is coming from this curve. So that x is the same as now square root of y. And so that now pi square root of y squared and minus pi, the small r thereon, that x is now from this one, that x is the same as here y over 2. So that pi y over 2 squared. Okay, so the volume is same as integral from 0 to 4. Y is moving from 0 to 4, and pi here square root of y squared is y minus, and that is pi over 4, and we make 4 here, and y squared and dy. Okay? Now, from now on, it's not difficult for you to finish the computation. So try to do it by yourself. Okay, this is the end of the section. Thank you.